Well, hello and welcome to Class 18. All right, today we're going to look at a topic that we've touched on before. Really early on in the class, Lecture 1 or Lecture 2, we looked at those attempts at fixing that concurrent update problem. And we ran into some that just locked up. And that was a case where we talked about that, either being Deadlock or Livelock. And we're going to talk about those two topics today and spend a little time investigating what's meant by each and what do you do about it? How do you detect that something like that is possible? What is it? What conditions allow for things to lock up like that? And being able to understand what those conditions are and eventually have a way to deal with that is important if you're designing a large concurrent system, especially where you have things like locks, where something is locked, something accesses, something unlocks. How do you make sure you never have a situation where everything locks up and you can't make any progress? So let's take a look at that. So if you'll remember from back in those early lectures, there are two aspects to the correctness of a concurrent system. And the first one's the safety property, and that means that nothing bad will happen, such as data being corrupted or an incorrect output. And the ATM problem where it lost a transaction and suddenly the $500 deposit was missing would be a violation of the safety property. Also, that ornamental garden problem that we saw with the turnstiles, with one entry turnstile, one exit turnstile getting a wrong value at the end of the day and saying there were -1 people left inside the property. That would also be a safety property violation. So safety property usually deals with the algorithm completes, but the results of it are corrupted or wrong or otherwise flawed in some way that is not giving the correct result that's intended because of some sort of concurrency problem. That's not, and notice the safety property is not the same as just an algorithmic problem where you just were a bad programmer and you had an off by one error or something like that. I guess you could consider that a safety property, but in this case, it's something, since we're in concurrency class, we're thinking of it as some shared value gets corrupted in some way. Now, what liveness is that means essentially that liveness property is stating that something good will eventually happen. And notice that if a program locks up and can never produce a result, it's not a safety property violation. Nothing got corrupted or the answer was wrong. It just never gave an answer. So that is a violation of liveness property if your program locks up and can't continue. So that's what we're going to be focusing on today, is kind of this liveness property and what kinds of things can violate it. How do we avoid that? Okay, so there are two main categories of what would constitute a liveness violation. The first one's deadlock, and that in deadlock, essentially we have a set of processes, we'll call that set S, and it's considered to be deadlocked if every process in S is blocked on an event that can only be caused by another process in S. So in other words, you have some set of processes. It doesn't have to be all the processes that exist, but there's some set, could be a subset of all the processes, and every one of them is blocked, waiting on some event that will only happen if other processes in S allow them to happen. Livelock is essentially very closely related, but there's a difference between this. This one, notice in deadlock, the processes are all blocked. They're stopped. They're not actively consuming resources. Livelock, you have a set of processes S, and they repeatedly enter the same sequence of states without producing useful work, and will repeatedly continue to do so. So notice there's a difference between these. Is deadlock, the processes are kind of suspended, waiting on something. Livelock, they're actively doing something, but the thing they're doing is the same sequence that depends on one of the other ones doing something. So note that they're closely related, but not quite the same phenomenon. In some cases, you could consider Livelock to be worse because while it's not going to ever make progress, it's also consuming CPU resources to do that. Deadlock, also terrible and catastrophic. You have a set of processes that are all blocked, not getting CPU time, not actively consuming resources. but blocked, meaning CPU resources, but still blocked and never going to make progress. But either way, deadlock, livelock, you're never going to make progress. There's another related behavior called starvation, which is similar to livelock as well. Starvation is basically you have one or more processes that just never get the resources they need to complete. And that could be that the resources are available, but other processes have a higher priority and are more frequently taking that. So that's a related thing where you never make progress on some process, but it's because the resources are already being taken or consumed by another thing. So, but we're going to focus on deadlock and livelock today. So let's start with deadlock. So for deadlock to exist, there are 4 conditions that are required. And those 4 conditions all have to be met. Notice it says required there. All 4 conditions have to be met in order to get in a deadlock state. So number 1, processes claim exclusive control of some resource. For example, a lock. Only one process at a time can have the lock, can acquire the lock, and then they have to release it before another one can get that. So in the case of a lock, is exclusive control of that. But it doesn't have to be just a lock. It could be exclusive control of some piece of hardware. Like, for example, right now as I'm recording this lecture, the recording software is using the camera that you see me in up here. And if I tried to run another application that needed the camera, it would say, I can't access the camera. It's being used by some other thing. It could even be a file. If you've ever opened a word processing document and then you try to open it again while it's still open, you might get an error saying you can't open this because it's locked by some other application. You're not allowed to use it. Or some sort of other piece of hardware like a serial port or another USB device. This device is already in use. You can't open it. So this could be a lock that's more of a abstract concurrency control here, or it could be a piece of hardware that has only allows single use access by one process. All right, number 2, processes hold resources while they're waiting. In other words, while they're waiting for some other resource, they hold on to the ones that they already have. Think of an application that needs the microphone and it also needs the camera. It allocates or acquires the camera, and then it says, I also need the microphone. The microphone's not available. I'll wait here, but I'll keep the camera while I'm waiting for the microphone. All right, number 3, resources cannot be taken from a process. In other words, you can't force a process to give up a resource. Once it has it and it belongs to it. And the only way to force it to give it up would be to kill that process. And then the 4th one is a circular chain of waiting exists. In other words, you have one process waiting on a resource that another one has, which is waiting on a resource that another one has, and eventually that comes back around to waiting on the first one that's waiting on the next one. So note in this case, each process is holding on to something that another needs, but that process is also waiting on another, and that loop goes around in a circle where they're always waiting on something and they're stuck there. All right, here's something that might make that a little more understandable. Here's a real-world example where you have this intersection where cars are trying to turn right, and they're at an intersection that looks like this. And there's actually one right down the street from the university here, an intersection exactly like this down at the end of, what is that, 2nd Street, I guess it would be. So if you walk down the street from the university, you can see an intersection just like this. So the stadium is up here where the baseball field is, and this football stadium. But if you look at this thing where you have this offset thing, you can have cars going north, in this case the white car is going north, trying to turn left, a string of cars going south, trying to turn right. Maybe this is people leaving the baseball game, maybe this is people trying to get to the football field. But you could have this situation where it's like that. So you'll notice that how does that meet the 4 conditions? Well, let's look at it. Exclusive control. Yes, this car right here has exclusive control of that physical spot on the road. You can't share that physical spot on the road without crashing the cars into each other. So each car shares its physical location on the road. Do they hold on while they're waiting? Yeah, a car doesn't disappear while it's waiting to move forward. It's stuck where it is, waiting to go forward. So this car, for example, the white one in the middle there, is stuck on the road while it's waiting for a car in front of it. Resources can't be taken. Well, there's nothing that can force them out of that spot. There's no third party that comes in and magically attaches a crane to the car and lifts it up out of there or pushes it out of the way. It sits there for as long as the driver of that car decides to sit there. And a circular wait, yeah, you can see the circle right here. This white car is waiting on that red one, which is waiting on this red one, which is waiting on that white one, which is waiting back on the first white one again. So there's our circular wait right there. So this meets all of the four conditions, and I have seen this happen down the street here at the end of the block. When there was a busy event down there, there were people leaving it, there were people going to it, and this has happened. Now, in the real world, this person in the front here eventually gave up and went forward and broke the deadlock, but imagine that that wasn't possible. You could have cars here waiting forever if this person didn't eventually give up control. And they said, well, I'm turning left, I'm just going to wait. I've also seen this happen in other places, not just down the street, but in other larger cities where you have people in bumper-to-bumper traffic. And this is why you don't act like a moron, and when the light is green and the intersection is full, you don't just go into there and block it, because then the other light changes and nobody can make progress. So, but I have seen situations like this happen in the real world with deadlock like that. Okay, now let's look at another deadlock example, and this is kind of a fun one. It's also a classic deadlock example, and this is called the dining philosophers. So here we have the philosophers are members of the department here, and each philosopher, they work like this. So that you have this table, and on the table we have plates of spaghetti, one in front of each of the philosophers, and then we have the same number of forks going around the table. But the idea is that in order to eat the spaghetti, you need to have 2 forks. So you need to kind of stick the forks in, twirl it up, and then eat it. So you need 2 forks in order to dine. So here's what the philosophers do. They think for a while. They're sitting there thinking philosophical thoughts. They pick up 1 fork. They pick up the other fork, so they have 2. They eat for a bit, and then they put both forks down, and they go back to thinking. So they repeat, go back and think more. Okay, I'm ready to eat a little more. Pick up the left fork, pick up the right fork. Doesn't matter the order. Pick up one, pick up the other one. Stick them in, twirl up the spaghetti, eat, put it down. Repeat until the spaghetti is gone. And as far as I know, this has not happened right down the street. Although maybe similar intellectual things have happened during department meetings. But the idea here is that each of the philosophers, like here's me at the top, they need to have both forks. And they pick up one and they wait for the other one if it's not available before they can eat. So they need both to dine, but they acquire them one at a time. All right, so let's think about what could go wrong with that, because it seems to make sense. There's enough forks to go around. Everybody can have 2, maybe not at the same time because they can't share one, but there's nothing here that they're all going to necessarily lock up. But think about what can happen here, that each philosopher does this. They think for a little bit, and they pick up some fork. Then they pick up the other one when it's available. They eat for a little bit, they put both forks down, and they repeat until then. So looking at that, it seems to make sense. When you're ready to eat, you get 2 forks and eat, and then you put them back. So how can that deadlock? We know that it can, because otherwise we wouldn't be talking about it here. So how? What's the process by which that can deadlock? Well, think about that each just gets done thinking at the same time, and they each pick up the fork, let's say, on their right. So I reach over and pick up my right fork, Travis picks up his right fork, Jim picks up his right fork, Dwayne and Jason pick up their right fork, and now we're all holding 1 fork. And now, then each says, well, in order to dine, I need the one on the left. And they sit there and they look at the space on the left, and they're just going to wait until the person who has it is done with it. And note that they'll be waiting forever because they all picked up the fork and they're holding on to it while they're waiting. So nothing in the sequence has anything to do with them waiting at that point. And how does this fit the 4 conditions? Well, it should be pretty clear that exclusive control of a resource. Yes, they cannot share a fork. Once they have it in their hand, it's theirs to use until they're done with it. Do they hold it while waiting? According to our algorithm, they do. When they're waiting, they hold on to the one they already picked up. Resource can't be taken. taken. Nothing in the algorithm said somebody watches these idiots sit around the table and comes up and punches one of them in the face and takes the fork away, or taps them on the shoulder and politely says, "Put your fork down." So that doesn't happen. That wasn't part of the algorithm we had. And is there circular wait? Well, not always, but there certainly can be in this case. If they all picked up the right or they all picked up the left at the same time, we'd be stuck there with them waiting in that circular loop. All right, so how do we prevent, and one thing, this seems like a silly example, and it kind of is, but think about this as not necessarily being just resources like forks around a table, but if you think about this as another kind of resource, like a certain process needs the camera and it needs the microphone in order to run, or a certain process that's doing some kind of GPU computing needs to access the graphics processor in order to do its computation, but other processes are vying for that as well. Or a certain process needs access to a printer to print out some sort of stuff, but not only does it need printer, but it also needs some other network device or something like that. So think about these resources as being something in a program, and this makes this a little more applicable to the real world. Or think about it like we did with locks. Like if you have, let's say you've got 3 different shared variables that all need to be accessed, like in a bank account. You need to take money from this account and transfer it to this one. Well, you need to acquire a lock on the first one and a lock on the second one. So you need to acquire a lock on bank account 1, acquire a lock on bank account 2, and then transfer the funds and then release those locks. Well, imagine another process is doing the same thing, but it's doing it in the other order. It's acquiring a lock from this one and that one, and if they both acquire the one lock first, and then they're going to try to acquire the second one, they'll both be stuck there forever. All right, so how do we deal with those situations that can come up? Well, there's 3 possible ways to deal with deadlock. And one thing to note is this applies to Livelock as well. Livelock is very similar to Deadlock. It's just they're actively continuing to run as they're locked up. So what are the ways of dealing with it? The first method is what we'd call deadlock prevention. And what deadlock prevention is, it's designing the system in such a way that it eliminates one of the 4 conditions, because we need all 4 of them in order for deadlock to occur. If we take any one of them out and just design the system where one of the 4 can't happen, then you'll never have deadlock. But that can have some negative consequences as well, as we'll see here in a second. Also, deadlock detection and recovery is you allow deadlock to occur, but when you have some kind of like a process that monitors it, and if it detects deadlock, then it breaks the deadlock and then attempts to recover from it. And then the last one is deadlock avoidance, and that's kind of the more intelligent way of dealing with this, that you allow all 4 conditions to occur, but you allocate resources carefully. In other words, you have sort of a resource allocation manager, and it decides who to give what resources so that you don't end up with deadlock as a possibility at any time. So we're going to take a look at each of these 3, deadlock prevention, deadlock detection and recovery, deadlock avoidance, and we're going to look at each of those one at a time in a little more detail. So let's start with deadlock prevention. So deadlock prevention, remember the idea there is to design the system in such a way that it eliminates one of the 4 conditions. And here are some of the options for doing that. So don't allow exclusive use of resources. In other words, don't allow resources that cannot be shared. Sometimes possible, sometimes not. For example, it would be hard to share the camera resource and have 2 different programs accessing it at the same time. It would be hard to, in the case of the dining philosophers, how do you really share a fork so 2 people can use it at the same time? It's really difficult. Or if it's a tool on a job site, you can't really have 2 different workers using the same hammer at the same time. It just doesn't make sense. So if you can do that, then if you can make it so all resources are always shared, then no deadlock will occur. All right, the second bullet there, all resources are requested and granted at once. Now that one you can do. You can say, all right, well, if you need to finish your job, a hammer and a saw, you got to get them both at the same time. You can't get the hammer and then get the saw later. And that gets rid of the circular wait, because you'll never be holding on to a resource while you're waiting for another, because you either have everything you need or you have nothing that you need. And then the other one is to release held resources while waiting on others. So in other words, you have the hammer, you need the saw, and you look, well, the saw's not there. I'm going to put the hammer down while I wait. And when the saw shows up, then I'll pick up the hammer and I'll pick up the saw again. The last one is to create a linear hierarchy where you give kind of like a, you can think of it like a priority level to each of the resources, and you require them to be allocated in the order of their hierarchy. And that means that if somebody needs the hammer and the saw, they'll always get the hammer first and then the saw. You can never have a circular wait because nobody could have the saw being waited on and be waiting on the hammer. Same thing could be true for the bank accounts. If you have two bank accounts and they both need to be locked in order to transfer funds, you lock the lowest account number one first, and then you do the higher one after that. That would eliminate the problem of one of a circular wait. So note that some of those can be impractical or inefficient. So for example, impractical, don't allow exclusive use of resources. That's a bad idea, especially think about the bank account. If you say, hey, everybody just access the bank accounts, let's make them all shared, then you could have that corruption issue with the concurrent update problem that we had. We need to have locks and synchronization. So we would probably want to fix that and allow them to lock the account while they're accessing it. Other things that would make this inefficient or impractical, all resources granted at once. Well, let's say you're on a job site and you need a hammer, a saw, and a welding unit. But you only need the welding unit at the end of the day, at the end of your shift. But the rule says when you check out resources, you got to get them all or none. So you get all of them and you hold on to that for your 8-hour shift, not using it all until the 10 seconds or 10 minutes at the end when you weld something once you're ready to. And that is inefficient in that nobody else could be using that tool while you're kind of hoarding it, even though you only need it for a short period of time. All right. Now, deadlock detection is the second one we said. Allow the conditions to exist, but have some kind of monitor process that looks for the deadlock and then does something about it, or detects it and then decides how to resolve it. So the general idea is to look for the circular wait. So the way we can detect that is, I'm going to present a method here. This is kind of an algorithmic method for detecting deadlock, meaning that you could get write a program that does this. But you'll notice that if we look at how the things are allocated and who has what, who's waiting for what, we could detect that circular wait. So let's look at how you do this. So we'll start with this concept of a resource allocation graph. So we're going to draw like a picture of who has what and who's waiting for what. So these squares are going to be processes. So P1, that's a process. Resources we're going to describe as circles. And inside of that circle is an individual resource of type R1. So R1 is a type of resource. The inside circle here is an individual resource that's available. So here, if I draw on my graph this, P1 with an arrow pointing to R1, to the outside circle, that means P1 is requesting one of type R1. If I have an arrow drawn this way with R1, the inside arrow pointing at P1, that means a resource of type R1 has already been allocated to process P1. So the process pointing at the thing says, I want one of those. The resource pointing at the process says, I belong to that process there. So to make this a little more complicated, let's add some things. So here's process 1, here's resource 1, and there's only one individual resource available. So P1 is requesting. Resource of type R1 has been allocated to P1. And then here's a more complicated one. P1 wants one of R1, but the one that was available has already been allocated to P2. So notice P1 is waiting for one to be available, but there are none available inside of that there. And here's a circular wait over here. P1 wants one of R1, P2 wants one of R2, but R1 is allocated to P2 and R2 is allocated to P1. So here's a circular wait. That's deadlock right there. They're all stuck waiting. Nobody can complete because they're holding on to the resource of another one. Okay, so here's what we do to detect that in that graph. Is the idea is to perform a reduction of that resource allocation graph. And we're going to do that like this. So first off, if all of the resource requests of a process could be granted, then we say that the graph could be reduced, that process could finish, and we can reduce the graph by that process, meaning take that process out of the graph. Reducing by a process assumes the process finishes. We don't really have to wait for it to finish. We're going to say, hey, it has everything it needs. Let's just pretend that it did finish, even if it hasn't yet. And we can take it out of the graph. And then when we take it out of the graph, we release all of the resources that it held. If a graph can be completely reduced, then there is no deadlock. If a graph cannot be completely reduced, then we know there's a deadlock condition that exists right now. And the set of processes that remain that are irreducible are the ones that are involved in the deadlock in some way. Now, one of the things to note, though, is while a system is running, we'd have to perform that resource allocation reduction every time resource requests change to say, anytime anybody acquires something or wants something and has to wait, we have to say, oh my God, is the system in deadlock? And if it is, then we say who's causing this. And once we know who's causing it, we need to decide what to do about it. We need to recover from it. Okay, so here's an example. So here's our graph. And again, arrows out of a processor requests, arrows into processes are held resources. So right now, you'll notice none of them have all the needed resources. So here's process 1 is waiting on something. So in other words, if you have an arrow going out of a process, it's waiting for something. Process 3, waiting for that. Process 4, waiting for that. Now, looking at this graph, though, could any of them get all of the needed resources? Well, here's an example here where there's an available resource. R2 has one that's unallocated. So notice that there are 3 processes trying to get that resource, and there's one available, so that could be granted to P2, P3, or P1. So P1, P2, or P3, all of them could have that granted. So let's give it to P3. That's the only thing it needs. So we give it to P3, and then we could reduce the graph by P3. So P3 is now done. We just assume that it is completed. We said, hey, if I gave that to them, they could finish. And so now we have, do we have any resources available? Yeah, we've got that available. We could give it to P1 or P2. Let's just give it to P2. So we give that to P2. Well, at that point, P2 already has these 2, and it only needs that 1. So that would allow P2 to have all the resources, and it could finish. And so now P1 can get both R1 and R2, and then it would have everything it needs. And now P4 can get R3 that it was waiting for, and it can complete. So the entire graph was reduced, so there is no deadlock. And again, if you can reduce the entire graph using this methodology, then we know that there's not any kind of deadlock. All right, let's look at a different example. So here we've got 4 processes, P1, P2, P3, P4. We've got 4 different resources, and all the resources only have 1 of each. So notice that P3 could get R3 and complete. So P3 is right here. It already has R4. It could complete by getting R3. So we can reduce it. P4 can now get R4 and R3. So P4 could get, there's that available and that available. It could get, it's like its hands reaching out. It could grab both of those and it could complete. But now we're up to these ones. P1 could get R3, but it can't get R1 because that's being held by P2. And P2 can't get R2 that it wants because that's being held. So I can't reduce any of these. Neither of these processes can get everything they need to complete. So now we've detected deadlock, and we know of those 4 processes, P1 and P2 are the ones that are deadlocked. Those are the ones causing the problem. So now we have a way to detect deadlock by using that. And that, interestingly, that reduction mechanism will work no matter what the resource is, no matter how many of individual ones are available, no matter how many processes. We could have 100 or 1,000 processes. We could go through this reduction. And if we get down where it can be completely reduced, there's not any deadlock right now. If we get, and this isn't actually watching the processes complete. This is kind of saying, hey, that one could finish. Let's pretend it does. That one could finish. Let's pretend it does. And if we can go down that chain and all of them could finish, there is not currently a deadlock. But if we go down that chain and we find out that some of them are left, we know there's one or more deadlock situations occurring. We need to figure out what to do about it. So what do we do about it? Well, we engage in what's called deadlock recovery. And deadlock recovery, really, there aren't a lot of options here. The options are killing the processes, or one of the processes involved in the deadlock, and then seeing if the deadlock remains and continuing to do that until it's not still there. And notice that that's not ideal, because there's a process that has acquired things. It's trying to do some work. It's trying to complete some job that is, in theory, relevant to our application, and just killing off processes like that and having them not able to complete their work isn't ideal. Another option is resource preemption, meaning that while they're waiting, you force them to give up one of the resources they're holding on to. And really, that's also not always possible and not always ideal, because they might have already done some work. Or let's say they have a printer and they've printed out several pages of something, and they try to access an account, and now they're in a deadlock situation. And you say, okay, well, I'm going to force the printer away from you, but they've already done some of the pages. How do you resume where you left off after that? And so there are problems with each of these. So the deadlock detection and deadlock recovery are not ideal, because we can either lose work and have to restart a process, or it could be not possible to always preempt some resource take a resource away from a process that's holding it. So one other thing to note about this deadlock detection recovery is there is overhead associated with that reduction algorithm. And especially since it has to be recomputed every time there's a change in resource needs. So anytime somebody requests a resource, we got to say, all right, is this system in deadlock? Anytime somebody changes what resource they're trying to access, we got to say, oh my God, is there a deadlock? And there is an alternative approach that uses a timeout-based resource allocation. In other words, you hold on to a resource while you're waiting, but only for a certain amount of time, and then you have to give it up. If a resource or lock waits longer than an expected period, we can stop and then report deadlock, or release all the locks of the process that timed out and restart it. And the problem is we don't know how long necessarily we need to wait. And the other problem is the system could just be slow and not deadlocked, and we would end up killing a process that was actually making progress when it was just waiting on something to be available because some other process was taking a long time to access it. And the other problem is with that approach is that something could be halfway done and then we preempt it. And so that could also be bad. So deadlock detection and deadlock recovery are kind of like the catastrophic approach. If we think back to that car example with the thing, it's like you have a police officer standing there, and he periodically looks over, and if he sees cars there and they've been there for a while, or they're waiting in a circle, they go and they like murder one of the drivers and then just shove the car out of the way and say, oh, hey, deadlock, problem solved, right? So society is much happier now because there's no deadlock with people waiting forever. When in reality, some driver has been forcibly removed from their existence, would be a nice way to say it. All right, so let's look at a more, intelligent way to do this. So the idea here is deadlock avoidance. Because deadlock prevention, removing one of the four conditions, that works. But it can also lead to non-optimal processing. We're holding onto resources when we're not using them, and or something like that. Deadlock detection or recovery will work as well, but it maybe is not optimal. So let's look at a version of this called deadlock avoidance. And with deadlock avoidance, what we do is we allow all four conditions to exist. We don't get rid of one of them, but we're careful with which allocations are granted. So the idea is just because a resource is available and a process wants it, we don't just necessarily give it to them. We look at, if I give you this, will that create a situation where deadlock could happen? So in other words, we never grant a resource request if it could lead to deadlock in the future. But the question is, so it's kind of like an intelligent way of allocating resources. But the question is, how do you do that? And so how do you know if it's going to be, if giving this resource to this process is going to lead to something dangerous or not? And the idea is that each process declares their resource requests at startup, their maximum resource requests as the process starts up. In other words, this process says, I'm going to need this account, I'm going to need that account. I'm going to need the camera, and I'm going to need the microphone. Now, I don't need them both right now, but I'm eventually going to need both of those. So they have to state all the resources they need before they actually perform the request. And so the idea here is we're going to define system states where we have safe, which is not deadlocked, and there's no possibility of deadlock, even if all the resource requests for the maximum are allocated. And then we have unsafe, which is not deadlocked, but if everyone asks for maximum resources all at once, deadlock could occur. And then deadlocked is the final state, and that's where a deadlock has occurred, just like we saw with deadlock detection. So to track this, we're going to use some data structures to do that. So here's what we're going to track. We're going to track an existence list, and meaning how many of each type of resource exists. For example, 5 file handles or 5 files that are open, 8 network sockets, 1 keyboard, and so forth. So each resource type has its own number of resources that are available in the system. So in this case, if there's 5 open files we can handle, and you might think, well, that's silly, you can open as many files as you want. Realistically, behind the scenes in the operating system, there is a finite limit to those things. How many total files can be open at once? There's a limit to that. How many network sockets can you have open all at one time? There's a limit to that. And if you're doing coding on an embedded system, which I do a lot of, then the resources get much smaller. Like, for example, how many network socket buffers are available? Well, that could be a fairly small number. That could be 4 of them or 2 of them or something like that. So here, the existence list, we're going to shorten that to EL, and it's going to say, and you don't necessarily think of this as file handles and network sockets and keyboard. Just think of it as resource of type 1. There's 5 of those in existence. Resources of type 2, there's 8. Resources of type 3, there's only 1. So you might have a resource existence list that's 1, 1, 1, or 2, 1, 1, or something like that. This is just a list of resource type is the index, and the quantity available is the number that's in there. All right, AL is the available list, and that's stating how many of each type of resource is free, how many are available right now. So the existence list is how many total exist. The available list is how many are available. So in this case, 340 means there are 3 files still available. And this is a typo here. This should say, let me change that to a 3 to match what it says there. So this is saying I've got 3 file handles available, I've got 4 network sockets available, and no keyboard. Somebody's already using the keyboard. All right, CA is current allocations. That's how much of each resource each process is using. And then MA is the maximum allocations, how much of each resource each process might eventually need. Okay, so here's how deadlock avoidance is going to work. So let's suppose, using that file sockets keyboard thing, our existence list is 5, 8, and 1, and our available list is 3, 4, and 0. So now we have 4 processes, A, B, C, and D, with their current allocation and maximum allocation as follows. So here's process A. Its current is 1, 2, and 1. Its maximum is 1, 3, and 1. And notice this F, S, and K, that's files, sockets, keyboard. I've just shortened that there. All right, so process B, currently it only has a file and no sockets and no keyboard, but it's going to eventually need 2 files that it has open at one time. And then down here for C, it doesn't have any files. It has 2 sockets open. Doesn't have a keyboard. It's going to eventually need 2 sockets and 1 keyboard. And then in here with D, 0, 0, 0. It doesn't have anything right now, but it's eventually going to need to open 2 files. So if all processes suddenly requested the max, could they all finish? If the answer is yes, then that would be a safe state. If the answer is no, then it's an unsafe state. So let's take a look at it. So is that previous state, is this state safe? Well, let's look at it. So, well, how much could each request? So we can compute the maximum allocation minus the current allocation. That's how many they could request, as they're all up to their maximum need. So here's their, basically we're taking this number, the maximum allocation, as I've switched these, and subtracting from that the current allocation. I'm doing that for each category. So 1 minus 1 is 0. 3 minus 2 is 1. 1 minus 1 is 0. So this one, the maximum request that it could make from where it is now to get everything it needs would be 1 additional socket. And we do that for all these. 2 minus 1 is 1. 0 minus 0 is always 0. So this could request 1 additional file. And then this one, same thing, could request 1 keyboard. This one could request 2 files because it doesn't have any right now. All right, but let's look at the available list. The available list is 3, 4, and 0, which I have over here. And we can observe here that A could get all of the resources that it needs. So notice there are enough available resources we could grant this request. Well, if we grant that request, then process A needs one of S, only one of S, 4 available right there. There's 1, there's 4. So now we could update AL by adding row A back to AL. So in other words, we could access the ones that it had back into the available list if it could complete. So in other words, this one could complete. So we could do what we did with a deadlock detection, say, well, if it could complete, let's pretend it did, and then it could allocate all of its back. So that would mean we would give back 1 of these, 3 of those, and 1 of those. In other words, the max allocation list. We're going to add that back to the available list, and now we'll have 4, 6, and 1. And now that we've added that 4, 6, and 1, then we repeat that process and say, well, now B could finish because it could get everything it needs. So we just go down the list and say, well, that could finish. If it finishes, we give all the resources it had back. Now we have 5, 6, and 1, which means that C could now finish. There's 1 available. C needs 1. And since it could finish, it could give all of its things back. And now we have 5, 8, and 1, which is kind of our maximum available. And now 2 could get its, or D could finish and complete. And if D could finish and complete and return its allocated resources, then we would be done. And we would have the available list equal to the existence list, 5, 8, and 1, and that's where it finished up. So that state was safe because there was a way that all of those processes could complete given the resources that were in reserve. All right, let's look at a different example. So existence list in this case now is 3, 4, and 1. The available list is, there's only 1 of those available. So here's the current allocations. 1, 2, 1 for A, 1, 0, 0, 0, 2, 0, 0, 0, 0. Here's the max allocations they're going to need. So if we take those, and notice this is the same CA and MA as before, but the only thing that's changed is the existence list and available list. We've reduced the number of resources that are available. So this is the same process as needing the same things. It's just we've said, well, we've recompiled this and put it on a system where there are only 3 files that can be opened at once. and 4 network sockets. Maybe we need to save memory, or we targeted a different processor or whatever. And note that this doesn't necessarily just mean computers. This could be tools of a certain type in a workplace. This is the number of hammers we have available. This is the number of saws we have available. This is the number of welders we have available, whatever. So notice the only thing we've changed is the number of resources that we have available. So is this state safe? Well, let's go through the reduction. Well, B can complete and return all its resources. Now are available, since it returns the ones that it had, maximum. It could get that one, which would give it 2 that it needs. It could complete, return the 2 back, and now we have 2, 0, 0. So, and notice the available list, in this case, didn't change because the current allocation of D was 0, 0, 0. So D could also complete. It would get those 2. It would complete and return those 2, but didn't have any. So it's not really putting any back. It's going to use those 2, but it could still complete. So now we have B and D completing, but now neither A nor C can complete. So our resource allocation list right now is 2, 0, 0. And what do they have now? The current allocation is this has 1 of F, that has 1 of F, but they need 2. They don't have their maximum allocation isn't met with what they have now, and they can't get it from what is available right now. And the big problem here is the S and K, that they both need that. So this system could deadlock and is therefore unsafe. Now, we don't know that it's necessarily deadlock, because they might give up one of those resources they're holding on to right now, but it's unsafe to grant any request right now, or it's an unsafe state right now. So we're going to use a system of deadlock avoidance that looks at, is a state that would result in granting a request, is that a safe state that results or an unsafe state? And this is what's called Dijkstra's banker's algorithm. And Dijkstra, you might remember him. We've seen his name before. He was kind of a computer scientist and mathematician. He was a pioneer in the area of concurrency. But he's the guy, the Dutch computer scientist who came up with semaphores that we saw earlier. If you remember, semaphores had those 2 operations, P and V, Proberen and Verhoeven, that were named that because he was Dutch. So he had a lot of contributions in the area of concurrency. This is his algorithm here. So, and this is called the banker's algorithm, because the idea is you never loan so much money out that you can't cover projects that are already going on and give them the money they're eventually going to need, because then if they call in and they need that to finish their project to pay you back, and you can't grant that, then nobody can finish their projects and the bank goes out of business. So the idea here is for Dijkstra's banker's algorithm, say when a process Q makes a request, so this is any process makes a request, we take the available list and we let AL prime, the available list prime, equal to the available list. We let CA prime equal the current allocation. In other words, we're making copies of the available list and the current allocation. And then we're pretending that the request was granted. So we update our copies of those 2 lists. We update the available list and the current allocation list. I should say CA there. Let me fix that. Okay, and then what you do is you compute the requirement prime, which is MA minus CA, and then act as if all processes are requesting maximum resources. So kind of like we did, we just say everybody requests their maximum resources at once. And using that requirement list prime, AL prime and CA prime, we see if there's a way to finish. In other words, we check to say, is the resulting state safe? And if it is a safe state, then we say, okay, giving this resource to that person was okay, I'll grant that request. But if giving them that resource resulted in a state that was unsafe, then we reject the request even though we have it. So in other words, you might be in the tool crib and somebody says, I need that screwdriver that I see that you have available there. And I would, rather than saying, okay, I have it here, have fun, I would say, all right, well, what's this worker eventually going to need? They have this, this, and this. They're eventually going to need that and that. If I did give them this, that could result in an unsafe state that would result in deadlock. So I'm going to say, even though I have this available, I'm going to say, no, not right now, because I recognize that. So the idea of this is really a brilliant solution. It's simple, it's easy to code, because we're just doing those checks and saying, hey, if I give this out, does that result in a safe state or an unsafe state? We have an algorithmic way to test for that. And it leaves all 4 conditions in place, but we're smart about the allocation. In other words, when a process requests something, we think, will that create a dangerous situation if I give this to you? If it does, I say no. Now, there are problems with implementing this. One of the problems is, how do we know ahead of time all of the resources that are needed? Sometimes resource needs change depending on the algorithm or the thing, so that might be a problem. We might deny some requests to preserve safety of the system or to keep it from deadlocking. And even though giving that out may not have resulted in deadlock, so we may reject a request even though we have a resource available just to maintain safety of the system. And the reason for that is we're essentially denying requests if there's any possibility of deadlock that could result, even if it's highly unlikely. Now, to finish up here, and I would encourage you to go back and look through how this works. It's really very simple. But one of the things that I wanted to mention here is Livelock. We talked about that in the first slide, and I want to mention it again here. And Livelock is essentially closely related to Deadlock, and I have here it's Deadlock's ugly cousin. And notice that the dining philosophers, there's a version of that where you say, well, while they're waiting, they put down the forks, and that would prevent deadlock from happening. So in other words, they pick up a fork, and if they look and the other one's not there, they set it down. We wouldn't get deadlock, but we could get Livelock from something like that. And Livelock can, like I said earlier, can be considered worse because you have processes consuming CPU resources while they're waiting. So it's kind of like zombies eating things in the environment while doing nothing productive. So you have these processes that are running and doing something and saying, hey, is it available now? No, I'll waste some time over here doing some computations and stuff. Is the resource available now? No, I'll waste some more time over here. So we're consuming resources while not making any progress on our eventual goal. And you could think of that like you make a multiplayer game and the players join it and they're all in a Livelock situation, but it's still rendering things on their screen and you're still seeing stuff happen, but it's saying, hey, waiting for the other players to join. And they're stuck there forever watching this thing saying, waiting for other players to join. It's never going to happen. And so Livelock, even though it's closely related, it still has its own 4 conditions. The only real difference between Livelock and Deadlock is in Deadlock, the processes involved in the circular wait are blocked waiting for something. In Livelock, they're checking, trying to actively get something, and maybe doing some other processing, rendering something in a spin loop, actively checking, is it available, is it available, is it available? And Livelock can be considered worse, but they're similar phenomenon. Okay, so that's all for today. Next class, you're going to have a lab where you're going to get to play with some Deadlock stuff. And I think I might make it so you guys are going to play around with a couple Deadlock examples and write some processes or maybe threads that deadlock, and you're going to see those deadlock, and then you're going to fix that using one of the methods that we talked about here. Come up with a way to fix that, but look for that next lecture. I'll go over the lab, talk about the lab, and then give you some time to work on it. So look for that for class 19. And that's it for today. And I met my goal of coming in under an hour. I talked fast through some of that. I would encourage you, if you need to, go back and look through the deadlock prevention, deadlock detection recovery, deadlock avoidance. understand the differences between those. There will be a final exam. As a hint, you'll probably be asked some questions about what the differences are between those. It'd be helpful to know the 4 conditions as well. And it'll be helpful to be able to do those graph reductions probably too. So look for that. And other than that, everybody stay safe, wash your hands, wear a mask, even if you've been vaccinated, at least out in public around other people that are vaccinated, you're probably okay. But I look forward to finishing up the semester, and then hopefully next year, next fall, getting back to normal, seeing you guys in class. I know it's been a rough semester having to do stuff this way. There are some advantages. You can watch the lectures multiple times. If you miss something, you can rewind and watch it again. You can, if you're the kind of person that is, I guess, cares about learning and wants to watch your stuff over and over again, you're certainly welcome to do that. So as always, let me know if you have any questions or problems with anything on the existing labs, and then look for that next lab next time. All right. Bye-bye.